All right, so I'm going to go ahead and begin. It looks like our attendees are starting to slow down a little bit, so I'm going to go ahead and kick it off and welcome everybody. My name is Nathan Dorr. I'm the curator here at the Draper Natural History Museum, and my assistant curator, Corey Inko, is joining us on the back end of technology today. Again, thank you all for joining us for today's virtual lunchtime expedition. We've got a full house for registrants today, and couldn't be more excited to have everyone joining us, especially our speakers today. Today's presentation is part of a new special exhibition here at the Center of the West, of the same name, What Lies Beneath, exploring Yellowstone Lake's mysterious events. The exhibit is open now and will remain open through August 8th. After a temporary deinstall, it will be back on view in October with a few special additions. So for those of you who are able to join us this summer to come and visit it, and you have a chance to come back October through May next year, there will be some great additions. A reminder that support for the Draper's Lunchtime Expedition series has been made possible by Sage Creek Ranch and the Nancy Carroll Draper Charitable Foundation. These sponsorships help make these programs possible. And of course, we're also grateful to you, all of our audience, for your attendance, your feedback, and your support of these programs. As I mentioned, we do record lunchtime expeditions and post them to our Draper YouTube channel. So if you've missed any of our previous speakers, you can find the presentations there. In addition to those of you joining us here on the Zoom webinar, we're also broadcasting today's presentation over on Facebook Live. So please, whether you're joining us here on the webinar directly or on Facebook, please feel free to submit your questions on Zoom. You can submit them via chat or the Q&A feature. And if you're over there on Facebook Live, feel free to add them to the comment section. We'll gather those and relay your questions to our speakers at the end of their presentation. So with that, today we are joined by Dr. Rob Sohn and Chris Linder from Woods Hole Oceanographic Institution. Rob is a geologist specializing in the study of hot springs and geysers. He obtained a BS in mechanical engineering from Purdue University in 1987, worked as an acoustics engineer from the Douglas Aircraft Company, and then obtained a PhD in oceanography from the Scripps Institution of Oceanography. He has been a research scientist at Woods Hole since 1999, where he has spent his early career studying deep sea vent fields, including several dives in the submersible Alvin. Chris Linder, our other speaker, specializes in photographing scientific fieldwork and wildlife in extreme environments. A former U.S. Navy officer and oceanographic researcher, Linder has photographed more than 50 scientific expeditions from Antarctica to the Congo. His goals as a photographer are to educate the public about environmental science and communicate the need to protect our planet's wild places. So without further ado, please welcome our May lunchtime expedition speakers, Rob Sohn and Chris Linder. Rob, I'll turn it over to you.
Thanks, Nathan. Let's see if we can make the technology work here. Okay. Well, I want to thank everyone for joining. This is really a unique experience for me. Like most or all of you, I went into some form of isolation a little over a year ago when the pandemic hit. And, you know, normally as a scientist, I do a lot of traveling. I'll give a lot of talks. But since then, I haven't done any traveling. I haven't given any talks. So this is the first time I've given a presentation virtually like this. So I hope you'll bear with me a little bit if my chops aren't quite up to speed. But I'm going to just try to give you a little bit of background on the science behind the project that Chris photographed spectacularly. I think you'll agree when you see the exhibit, which I hope you all will. But our project was called the HDY Lake, or Hydrothermal Dynamics of Yellowstone Lake. It's a relatively large by the standards project with various disciplines ranging from geophysics, geochemistry, paleoecology, geology, microbiology, and others. We did 3 years of field work in Yellowstone Lake from 2016 to 2018. So the last piece of kit came out of the lake about 2.5 years ago. And since then, we've been working really hard on the samples and the data to try to put together the scientific story. These lake floor hydrothermal systems, of course, you know, the thermal features in Yellowstone were stuff of legend and myth, really, in the Old West. People didn't believe the initial reports of, you know, water shooting from the ground and all this kind of stuff. But eventually, of course, that was all verified, and scientists, as you can imagine, have been very interested in Yellowstone's thermal areas ever since, you know, Western man, so to speak, started occupying the area. And there's a huge body of literature on the thermal features in Yellowstone, but the systems in Yellowstone Lake were only known to science in sort of a formal way about, let's say, 20 years ago or so. So these are thermal features. Of course, they're very hard to access because they're underwater, but they're also ones that sort of escaped our scientific knowledge for quite a long time. So we're trying to kind of make up for lost time here and really do as much studying as we can. And what we were trying to understand is how these lake floor hydrothermal systems respond to different kinds of perturbations or changes. For example, things like earthquakes, the changing climate of the region, the water column, the lake's water itself is constantly moving. How do these sorts of things influence and affect the hydrothermal systems? And you'll understand why we care about that better in just a minute. And before I launch into all that, I want to take a moment to recognize our major sponsor, the National Science Foundation. That means all of you supported this research, and I hope you feel good about it. This project probably cost the average person around 1/4 cent. So I hope you'll feel like your 1/4 cent investment is going to give a good return. But we're very, you know, sort of mindful that our obligation ultimately is to the taxpayer. We take that very seriously and try to produce the highest quality and the largest volume of research with the funding we receive. The U.S. Geological Survey, USGS, also was heavily involved in this project. And they provide a lot of in-kind support. A lot of their personnel they assigned or allowed to work on the project. They provided trailers that we stayed in over the field seasons and so forth. So I also want to acknowledge the USGS. And the other thing I want to do is just take a quick moment to recognize, you know, I'm sitting here as a scientist representing the project, and I get to, as the lead PI, tell you about what everyone else has been doing. 99% of the time, being the lead PI is a pain in the you-know-what, but there's a few moments like these where I get to sort of bask in the glory of the work that this incredible team has done. And there were more than 10 different academic and federal institutions, private, public, and otherwise, in the US and Europe that were involved in this research. And the sort of idea, you know, kind of one of the selling points when we were pitching this project to the Science Foundation, what we really wanted to do is bring together kind of two distinct groups of people. On the one hand, we have people who are absolute experts in Yellowstone science, particularly with respect to thermal areas. And on the other hand, we have people who are the absolute world's experts in using deep sea technology to study things like hydrothermal vents, you know, in the deep sea. Clearly, having these vents on the floor of the lake's pretty deep. It's over 100 meters deep. So, you know, you can do your math, but let's say 340, 350 feet deep. So it's very deep. You can't just jump in the water with a snorkel and a mask and go look at the vents. And so this project really represents kind of a union or a coming together of those two communities to really try and advance our understanding of the lake. So I just want to give a little kind of brief background on the thermal features in Yellowstone in general, to give you a sense of why it's so important to study the ones in the lake. And if I hope many or most of you have been to the park, and if you haven't, get there as fast as you can. It's one of the most spectacular landscapes anywhere on Earth. And one of the things that makes it so spectacular is the wide variety and incredible quantity of thermal features that you see when you go through the park. And more than 10,000 thermal features have been documented in Yellowstone. And there's an incredible variety, and this graphic attempts to illustrate that. And first and foremost, you have to understand that the only reason any of this is happening is because there's magma in the crust beneath Yellowstone, and there's quite a lot of it, actually. It's a very large body of magma. In fact, scientists who really study this will tell you there's actually two distinct bodies of magma. But that magma is providing all the heat that drives these thermal features. So that's the most fundamental aspect in a sense. Then once those those natural waters get heated, and they also exchange minerals with the rocks, then they'll start percolating up. They might have to go for, let's say, 3 miles through the crust vertically to get from the zone where they get heated up until you can see them as one of these brilliant thermal pools or whatever. So it's a long journey, and a lot can happen along that journey. And depending exactly on what happens and where, when they finally get to the surface, they could be manifested as a travertine, like you see in Mammoth in a very spectacular way. Mud pots, like in Mud Volcano, fumaroles, same thing. Geysers, incredibly enough, over half of all the geysers in the world are in Yellowstone National Park. Spectacular features that I've spent a lot of time myself actually studying. And then finally, over on the right side of this image, you see Yellowstone Lake. And again, as I mentioned, we've only known about these vents in the last few decades. But there's a whole nother class of vents that are underwater, under pretty deep water in the lake. And so now if we try to put that into context, on the left-hand panel, you have an overview of where the thermal areas are in Yellowstone in a general sense. You can see the lake there, it's sort of in the middle. That dashed dotted line is the outline of the 640,000 year Yellowstone caldera. So the last major catastrophic eruption drained magma out of the crust over an area roughly that size. So it's huge. Most volcanoes, you can stand on the lip and you can see the entire caldera. In Yellowstone, you can't do that. It's far too big. But the point I want to really make here is that if you go to Yellowstone, the scientists, we divide all the thermal areas up into two different classifications. And they're shown here on the left panel as green and black symbols. The green symbols are neutral to alkaline, so these are the sapphire pools and the geyser systems, and you can see that a lot of them are there in the upper, mid, and lower Midway Geyser Basin. And then the other kind are these acidic, steam heated. They're represented in black, and you can see that in general they're located in different places, but in point of fact they can be very close to each other. And so I don't want to hurt anybody with too much hardcore science, but if you want to understand the thermal areas in Yellowstone, you have to understand a little bit about this phase diagram on the right-hand side. And I just want to take a quick minute to kind of walk us through the fundamentals here. And on the left side, so we have pressure, increasing pressure on this axis, and increasing temperature on this axis. It's not a linear axis, it's a conceptual diagram. But, you know, when things are cold, they're solids. When they're in the middle, they're liquids. And when they're really hot, they're gases. That's a general rule of thumb. And, you know, here at 1 atmosphere pressure, where most of us live at sea level, and in Yellowstone area, you're a little bit less pressure because you're higher up. But we really experience this phase diagram on this x-axis. We experience one pressure and the temperature is going to change. And so we all understand this intuitively from a very young age. At a certain temperature, and Celsius scale is nice and convenient, 0, water freezes into ice. And then as it heats up, eventually at 100 degrees C, 212 F, it turns into steam and becomes a gas. And we all understand that. So the first thing I'll point out is that this boundary between a gas and a liquid, what you might think of as the boiling point, as you increase the pressure, that temperature goes up and up and up and up and up. So that water can persist as a liquid at very high temperatures if the pressure is very high. And on the floor of Yellowstone Lake, the pressure is approximately 5 atmospheres. So, or sorry, 11 atmospheres. About 11 times as much pressure as you experience walking around, which is actually quite a lot. And that changes the boiling temperature from 100 degrees C to 173 degrees C. It almost doubles it. So the fluids that are discharging into the lake, on the bottom of the lake, they're actually at temperatures up to 173 degrees C, which is about 343 Fahrenheit. They're hotter than you can imagine water ever being. They're incredibly hot. And that means that the hottest thermal areas in Yellowstone are the ones on the floor of Yellowstone Lake. And so that gives scientists the opportunity to actually sample and study these fluids before they've decompressed all the way to 1 atmosphere pressure, which is where we normally get to look at these fluids. So this is really going to the bottom of the lake is like getting this incredible window that is impossible to get any other place in the park into the very hot, sort of more primitive fluids before they fully separated out and boiled off all their constituents. So as hydrothermal fluids are coming up from that magma chamber very, very deep, they're coming up along this boiling curve, okay? And, you know, when they're deep, they might be 300 degrees or something, and they come up and the boiling temperature all of a sudden is much lower, and these fluids are too hot. And they are subject to the laws of thermodynamics, just like the rest of us. And so in order to stay in thermodynamic equilibrium, they have to lose heat, they have to cool down. And the way they do that is by releasing steam. So as these fluids are coming up through the crust, they're continually boiling off steam. And the magmas have a lot of volcanic gases in them, like carbon dioxide and hydrogen sulfide. And those gases, when the water boils off steam to stay in thermodynamic equilibrium, those gases go with the steam. And that separation process is what gives us these 2 different kinds of thermal areas. So the neutral to alkaline, like the geyser basins, these are the liquids that have stayed as a liquid the entire time on that journey from the magma chamber to the ground surface. And these acid or steam heated systems, these are the steam and the volcanic gases that have boiled off of these liquids. And then for reasons that we don't totally understand, they have different propagation paths through the crust. So that's the basics. There's 2 different kinds of thermal areas in Yellowstone. And now if we look at the lake, this red line here is representing that Caldera Boundary. So what you can see is that the northern and kind of northwestern part of the lake is inside the caldera. And then the southeastern part of the lake, the 2 arms in particular, are outside of the caldera. And sure enough, what we find is that all these hydrothermal vents, which have been mapped here, shown as pink dots, for the most part, except for this guy, are in areas that are inside the caldera, where we have that magmatic heat to fuel the circulation. And the reason that we're really interested in how the lake responds, or how these hydrothermal systems respond to changes and perturbations, is because they have a tendency to explode, which is a little concerning. Yellowstone Lake itself, it formed after the last glacier retreated from this area, something like 13,000 years ago. You know, if you want to get in a good bar argument with a geologist, you know, you can debate whether it was 13,000 or 14,000. That can be a lot of fun, but it's about 13,000 years ago. And since that time, and we know the number now much better because of work done on our project, there have been at least 16 hydrothermal explosions in the lake. Well, what's a hydrothermal explosion? A hydrothermal explosion is a situation where we have all these hot fluids, they can be liquids or gas or what have you, in the crust, and for some reason they decide to spontaneously explode. And some of those can be very catastrophic. And what you're basically looking at is, we're talking about, you know, being on this boiling curve, so these fluids here are in equilibrium, and somehow they get depressurized. The pressure on those fluids suddenly is released, and that pushes them up into this unstable field. And so the liquids flash to steam, the gases expand, and you have a major explosion. And there have been at least 2 really catastrophic events since the last glaciation. I'll just mention that, you know, you might think, well, how do you depressurize a fluid? And it's a good question. But the fact that these systems are on the floor of a lake and are covered with water is the big clue. And so you can move water around, right? And there's sort of 2 hypotheses. They don't have to be, you know, they can act together. But, you know, if you have an earthquake, and we know Yellowstone area is one of the most seismically active areas in the world, you have a large earthquake in the same way that an earthquake that's under the ocean can create a tsunami. An earthquake that's under the lake or very close to the lake can create a lake tsunami, where the water just starts sloshing around. You could think of it as a giant bathtub. You know, you could shake a bathtub or something. And that has the potential to move water very quickly. And that's a process that could easily depressurize the lake floor vents. And as I mentioned, the lake has been forming after the last glaciation, so the glaciers have been retreating. And there's also the possibility that, you know, you have these glacial dams that hold back water. And if you were to breach one of those dams, you could spill tremendously large volumes of water out of the lake very quickly. That's another way you can depressurize these systems. And this is an artist's rendering of the Mary Bay explosion crater. So this Yellowstone Lake in Mary Bay, I know at least one person is listening to this talk from Fishing Bridge Visitor Center, you know, in other words, under kind of the steam cloud in this photo, or this drawing. But this explosion crater is about 2.5 kilometers wide. It's over 100 meters deep, and it distributed explosion breccia materials over an area of 30 square kilometers. And it's the largest such feature in the world. I don't know if that makes us lucky to have it or not. But this kind of catastrophic event represents a very significant geological hazard for Yellowstone. And we'd really like to understand better, for example, what kind of things can cause an event like this. And so, as I mentioned, you know, one of the sort of key aspects of this project is bringing some really new state-of-the-art technology into the lake, tools that were developed for deep sea research. Our project in general, we sort of had a 2-pronged, if you will, approach. In order to understand this system, we put instrumentation on the lake floor to monitor the modern system, to monitor what's happening right now. And we also had a very extensive coring program where we sampled long sediment cores. And the way, you know, that works, there's diatoms that are continually falling out of the water column after they die, plankton basically, and they're creating the sediments on the lake floor. But then when something kind of geologically interesting happens, like a hydrothermal explosion, for example, that gets deposited in the sediments. And then, of course, it gets buried as more sediments pile up on it. So that these cores, they contain the geological history of the lake. And it's a tricky thing to interpret that. But anyway, our project had those two components. We had a modern day monitoring instrumentation, which is where really the high technology came in, and then a coring program looking at the history. So I'm just going to give you a little overview, and this is one of Chris's wonderful photos, by the way, of the technology. And the Global Foundation for Ocean Exploration built a research vessel, tailor-made, if you will, to Yellowstone Lake. There are restrictions about how large of a vessel you can have in the lake, for example. This research vessel is called Annie, and it's exactly as long as it can be and not an inch longer or shorter. And the Global Foundation really spent a lot of time designing this thing so they could do the most science possible given the restriction on length. And they did a wonderful job. So there's a state-of-the-art research vessel that can work in Yellowstone Lake now. It's a very exciting development. The other side to that story then is this remotely operated vehicle Yogi. And if we're talking about underwater robotics, you basically have two options. You can either put your robot on the end of a wire and control it from the ship, with fancy joysticks and stuff like that. Or you can have a completely free swimming robot where you program a mission, put it in the water, hit run and pray for the best, where you have no connection to the robot. We use both kinds in this study. And so Yogi is an example of a robot on the end of a wire. You can see the yellow cable there. That's not just any wire, by the way. That's very expensive wire. Don't step on it, okay? But Yogi, it has a manipulator arm that you can kind of see. It's furled up right now as it's getting in the water. But engineers on the research vessel it's a fully articulating, like 5 or 7 function arm with a wrist and a claw and so forth. So it can manipulate in a very fine way instruments or samples that you're trying to collect. It has super high-tech video banks, video cameras and so forth. And this is, so exciting that the researchers working in the park have access to this kind of truly cutting-edge technology, and it really made a lot of what we did possible. So this is just an example what it looks like in the control room on that research vessel Annie. Close all the doors, draw all the blinds so it's nice and dark. You can see the pilot there working the joysticks in the middle, and there's something like 6 different video cameras, so you can see in front, behind, to the side, and so forth. And then you've got a navigator who's in the foreground, and then a data guy who's in the background. And these 3 engineers are running this high-tech robot. You can see in the screen there, they're near the lake floor with the manipulator working. And I'm the privileged scientist that gets to stand behind them and say, okay, move over this way a little bit. No, not there. Okay, yeah, try grabbing that. Oh, try, so it's pretty good work if you can get it. And the other kind of robot that we use for this study is a free-swimming, fully autonomous. In the industry, we call them AUVs, autonomous underwater vehicles. This is an example here. This is a robot that's built here in Woods Hole at my institution. And you lower this thing into the water and you let it swim away and do its science. And you can actually go do something else while it's working, which is pretty cool. this is the same type of vehicle, by the way, that was used to find the Air France Flight 447 wreckage in the Atlantic Ocean in 2010. So, this is the top of the top in terms of robotic technology. And it was a real privilege to be able to use it in Yellowstone Lake. Then on the other side of the spectrum, you have the Coring project, which, if I'm going to be honest, that's some Stone Age tools. It's 2 Carolina skiffs that are rafted together with an aluminum superstructure, and then a coring rig that's not a tripod, but a quadrupod or a tower, I guess, that gets put up there with a pulley, and you take a 12-meter, 40-foot long or so pipe, you rig it up on that thing, you put a whole bunch of weight on it, and then you lower it down towards the lake floor, and when it's within so close, you free spool it and let it slam down, drive itself 40 feet into the sediments, and then you pull it back up. So there was a real spectrum of technology used on this project. I'm going to try to tell you a little bit about the results from each. And this is what it looks like when you pull up those cores. There's a plastic sheath that you end up cutting up into sections. Of course, you got to be careful how you label it, so when you get back in the lab, top doesn't become bottom or something stupid like that. But each of the sites, you end up with a length of core recording that sediment and geological history of the lake. So on the left panel, we have a map of Yellowstone Lake again. And what you can see is this area called the Deep Hole. It's not a very imaginative name, but it is accurate. It's the deepest part of the lake, and it's a hole. And it's about 2 kilometers southeast of Stevenson Island, right here. And this, by the way, is the explosion crater from the Mary Bay explosion that we were talking about earlier. And so this was what we called our focus site. This is where we deployed a lot of our instrumentation and really focused a lot of our efforts in terms of monitoring to try and understand what's going on. And on the right panel is an example of a map of this area that was made by the free swimming robot, where we're going from sort of 115 meters all the way up to 80. So this is like a 30-foot, this is 30 meter, 100-foot or deeper hole in the lake floor sediments that's created by the hydrothermal fluids that are discharging in this area. And these white triangles are places where we saw active venting with Yogi, the remotely operated vehicle. So you can see that, the whole, it's got kind of a length scale of maybe this particular one, 300 meters by about 200 meters. And you've got this intense cluster of hot fluids that are coming out of the lake floor, and then a little less intense as you move up to the north here. So what do those vents look like? They look like this. I could play a movie here for you. This was the Yogi dive video. So here you can see hot water coming out of this sort of crack or vent, if you will, and it's being populated by filamentous bacteria. These are microbes that eat sulfur. Doesn't sound like much fun to me, but that's what they do. And these are really unique life forms. There's a whole component of our project that's focused on understanding these bizarre heat, sulfur-loving life forms. Most of us don't necessarily like either. But I can't tell you a lot about it because I'm not a microbiologist. What I can tell you is that those filamentous bacteria share something with all of us right now, which is that they are being attacked by viruses. I can't tell you much deeper than that, but my microbiologist friends on the project assure me that these sulfur-eating bacteria are being attacked by viruses. So I guess nobody's safe no matter where you are. And one of the things that we did, which was really innovative, and this was the University of Minnesota team, designed a system that we could basically encase one of those areas where the fluids are coming out and put a sensor inside the vent that allows us to measure the temperature and composition of the fluid that's coming out of the lake floor over an entire year interval. And so if we're trying to understand how the system responds to changes, we have to measure the changes that are occurring and measure how the system responds. So this was a really key aspect of us being able to understand how these systems were responding. We could get this fluid composition and temperature data over an entire year interval. And this is kind of fun. So you saw in the previous movie what it looked like when we put that instrument into the vent. And this is a picture from when we took it, we came back a year later to take it out. Looks a little different. It's been populated by all these microbes, microbial organisms. It turns out, you know, they just needed a place to hang out. But the good news is we didn't let this go to waste. We sampled all of these organisms before we retrieved the instrument. And so one of the, you know, there's too many results. You know, if I had all day, I still couldn't tell you everything. So I just want to highlight a few things. And one of the results that's come out of this, and I apologize a little bit, this is an image from a scientific publication that's going to come out probably in the next month or so. So some of this stuff you're seeing before other scientists even get to see it. So special job. But what it's showing here, you know, this blue, this is the water, this is the lake water. Then the green here, this is the lake floor. And then this kind of thing here is this depression where the venting is coming out. And what we've found, and we've corroborated this through two completely different lines of evidence, is that underneath the lake floor, about 15 meters down, you have some kind of a cap, like a clay layer, very low permeability sediment material that has trapped a steam reservoir underneath the lake floor. So you think about that just for a minute. At the deep hole, about 15 meters, so let's say 50 feet below the lake floor, there's a large reservoir of trapped steam. That has implications, and what, if you want to think of it, you know, in kind of everyday terms, what you can imagine is there's basically a steam wand under the lake that's just continuously injecting steam into this area underneath the deep hole. And there's some kind of cap 15 meters down that's arresting that steam and trapping it and preventing it from sort of being flooded with lake water. And this is really interesting because, so that means that this is one of these vapor dominated fields. So when the fluids come up, the steam and gases that boil off, this is one place where they come out. But everywhere else in the park where we find these kind of systems, we find them at high elevations, high altitudes. And the thinking was that you could have this steam below the ground surface because the water table at the high altitudes was much lower than the altitude of the ground surface. So you could accumulate steam between the water table and the ground surface. And what we're found here turns that upside down and on its head, because now we have steam that's overlaying, you know, lying under 140 meters of water. And so how you can preserve, trap and preserve steam beneath all that water is a question, is one of the active questions that we have. We know it's there. We're still not entirely sure how it can be there. Then just to wrap up the science, I hope I've done okay with time here. I just want to say a quick word too about the coring program. Um, the sediment cores that we took, you can kind of try and imagine what it's like. We had 6 different sites where we took these sort of, think on the order of 10-meter long cores, and they each have their own kind of unique history, but we know they're all telling the same story, but you have to decipher it. And it's really hard work, and it takes a lot of dedication and, you know, like losing family and friends for a couple of years. I think the lead scientist who was working on this may have to reconnect with her family sometime soon. But at the end of the day, and this is also a figure that has not been published yet, so you're getting the sneak preview, getting a jump on the scientists here. There have been at least 16 hydrothermal explosions in Yellowstone Lake since the last glaciation, which, as I mentioned, was about 13,000 years ago. So that's, you know, averages out to a little more than 1 every 1,000 years. And one of the really interesting aspects of this research is, and our project has really laid this plain to see, is that there are very, very much 2 distinct types of explosions. And the most prevalent, and if you look on this chart here, it's these red bars, and this is, you know, the way geologists, the way we do it, Ka is 1,000 years before now, so 0 is now. And then you go back to the glacier and you can see all these small explosions. You know, some of them were like 100 years ago or something, so not that long ago. And these, you know, are small burps, is one way to think of it. And we think that these are associated with gas, you know, that steam reservoir. If you have gases suddenly escape from that reservoir, of course, they expand as they depressurize. And that could be a likely mechanism to explain these deposits formed by these very much smaller explosions. And then there's sort of a different class, the large catastrophic ones. And these, you know, these would be a real problem if they happen now. The last one in the lake, the Elliot's Lake, was about 8,000 years ago. The biggest one, Mary's Bay, was something around 13,000 years ago. And these are cases where you have hot liquid water that gets depressurized and flashes to steam. And a steam molecule occupies about 1,600 times larger volume of space than a water molecule does. Another way to say that is steam is much less dense than liquid water. But what that does, when you change liquid water molecule to steam, it needs to have 1,600 times more elbow room to move around. And that basically causes a huge catastrophic explosion. You blow all the material, the liquid itself that's turning into steam blows out, the ground, the sediments, the rocks that are encasing those fluids get blown out. And so, you know, there are 2 of those in the lake, and then, you know, some pretty big ones, Turbid Lake, which is right next to Yellowstone Lake, for those of you who are familiar, in Indian Pond. And so these are probably a very different triggering mechanism. In this case, you know, it probably takes something like a large earthquake that creates a lake tsunami. The breaching of a glacial dam, as I mentioned, I don't think we have to worry about that anymore. But the large earthquake lake tsunami scenario is definitely something that we need to be mindful of going forward. And that sort of does it for what I had planned. And, you know, if you have questions, I know we're going to answer those at the end. So I just wanted, as by way of a segue, say a quick word about Chris Linder, who's photographed here 3 different photographs. You know, I searched my archives. I've been working with Chris for over 20 years, and I couldn't find a picture of him without a camera in his hand. And I think that really kind of says the whole story in a way. But I've been literally all over the world with Chris. He's followed some of my other projects as well. And he is the hardest working guy in science photography. He gets up before the scientists. He goes to bed after the scientists. He's always running here, there, rigging up some new way to take a picture. It's remarkable how hard Chris works. And I think you're going to understand a little bit more about that when you get to see some of his photos. So with that, I'll yield the floor and let Chris say a few words.
Oh, thanks a lot, Rob, for the introduction. I'm going to share screen. Okay, so I'm going to take you through my side of the story, which is different from Rob's. I'm coming at this amazing scientific project from the perspective of a storyteller, or another way I like to think of myself as a science interpreter. So I use photographs and video to tell science stories, to make them more accessible and relatable to the public, and help them engage and ask questions of the scientists, and really help get the word out to the broader public about the amazing work that scientists like Rob and the team are doing in the lake. So I want to thank Nathan and Corey and all the team at the Center of the West for the beautiful exhibit that they created. I haven't seen it myself. I've just seen pictures of it on the walls. It looks fantastic. I'm really excited to someday get there and see it myself. It'll have 2 showings in Cody there, and I hope as many of you who are in the area are able to go see it in person and see it on the walls and enjoy it. The second exhibit is going to have some special artifacts that are also going to be with the photographs. I think it's 25 photographs on the walls, some interpretive panels, and we've also got some video that we're sharing with that as well from Yogi, the submersible vehicle. So a little quick bit about my background. As Nathan explained, I'm a former oceanographer. My previous job as physical oceanographer was to work on ships like this. This is the research vessel Oceanus in the Gulf Stream in winter. So my job was to kind of help get instruments over the side, bring them back, do data processing, work with scientists to get the results published. But over the years, I transitioned to photographing science. I've had the amazing opportunity to photograph the manned submersible Alvin here in the Gulf of Mexico. And then also those photos from the Arctic that Rob showed you. This is one of the photos from that project where I spent 6 weeks on the Swedish icebreaker Odin with Rob and his team looking for life in another set of vents, this time at the bottom of the Arctic Ocean, which was an incredible project and one that I will never forget. And so here's Rob being pressured to do a portrait when he's not wrangling scientists and desperately trying to get the ice to work his way on the icebreaker. Rob is a fantastic guy to work with, always tremendously upbeat, and as you can tell from the last presentation, adept at telling science stories himself, at taking complicated scientific data and making it really, really interesting and relatable to the public. So it was a real pleasure when Rob invited me to work with him again on the HDY project. HDY Lake project. I'd never been to Yellowstone before. So that was both, a treat and also intimidating to me as a photographer, because obviously so much photography has been done in this park. So many people visit it. But this was a unique opportunity to take a look at a subject that doesn't get a lot of photographic attention. I mean, let's face it, most of the attractions in the park have a heartbeat, or they're, spewing steam into the air at one of the geothermal areas. It's not really the lake. So I had an opportunity to tell stories about a part of the park that didn't really get a lot of attention. And then, of course, being embedded with the scientists, I got to tell a story of how they did their jobs, what tools did they use, how did they accomplish this mission under somewhat difficult circumstances. a lot of times. I want to show a couple of pictures of and examples of how I do my work and how I approach a story like this. One of the first things I do is work on establishing shots of what is this place like? How do you set the scene, if you will? You know, what is this environment like? I tried to capture the lake in all of its different moods, and it has many, many moods, as I found out from working on this project. This was, you know, a somewhat benign, beautiful day. You can see, just for a sense of scale, this tiny little dot on the lake is the coring rig platform that Rob showed that's taking cores from the bottom of the lake, just to give you a sense of scale. I needed that coring platform in this shot to give you an idea of the size. I mean, you obviously have mountains in the background, but this is a really, really big lake. And I wanted to get that across too, as this is, it's a unique environment. You know, it's very difficult to get a sense of what's underneath these waves. And in this case, this calm water on the lake. There's only a handful of spots around the lake where you can see active geothermal areas from just standing at, you know, on one of the boardwalks. And West Thumb is one of those places. So this is the feature called Fish and Cone. I timed it at sunset, and the moon was just coming up. It just happened to work out for this shot. Did a long time exposure to smooth out the water, to really focus our attention on that one feature. But I see this, I use this image as kind of like a hint of what lies beneath, just a little sampling of what's underneath that surface, and give this idea that this is a unique lake, and that it's not like others. It has this amazing geothermal system underneath it. There's very few places you can actually see something like this from the surface. I also wanted to show, you know, what this lake can be like on an angry day. And in the case of the research team, we were often going out in the research vessel before dawn, because this was a pretty typical condition in the afternoon on the lake when the winds built up. And when the waves are like this, it's too difficult to do work on the vessel on the lake. So we tended to be out on the water really, really early. Especially in when the coring project was going on. If you can think about, you know, trying to get a 30-foot section of sediment up from the bottom, 400 feet down, you know, on two skiffs that are joined together with that big apparatus on top. You know, you need absolutely calm conditions for that to work. But the lake was often like this. And the research team got chased off the lake a few times because of these wind and thunderstorm events that would blow up and create some pretty significant wave action on the lake. So one of the things I knew I also had to do in order to communicate one of the important features of the lake, these hydrothermal explosion craters, Mary Bay being the one that I absolutely needed to photograph. I needed to get up high and see it from above. And so I worked with this pilot, Chris Boyer, who I've known for a number of years. He donates his time to fly his little red plane through an organization called Lighthawk, which helps scientists and conservationists get an aerial perspective of their work. And so I had a great privilege of flying with Chris from Montana over the lake. We spent about, I think, an hour and a half flying over. Unfortunately, we had some really severe forest fire conditions. So visibility was absolutely awful. It was, you know, I was breathing in smoke when we were up in the air. We had the windows open so I could shoot out of an open window. But I managed to get a shot showing this this 2.5 kilometer diameter Mary Bay crater. You know, from the surface, from the road, you just don't get a sense of the scale of the size of this crater. And so this was an important image for me to make. Despite the forest fire conditions, I knew that I had to get a photograph that showed the scale of this crater to tell the story of the size of it. Also managed to get some top-down shots at West Thumb Basin, again showing this transition of just how active these geothermal areas are right at the lake shore as it's transitioning into the lake, and give you a sense of how the kind of terrestrial and the aquatic zones connect there. The stuff that you can see and that's really popular with the tourists in the park, and then the great unknown, which here is this big empty area of the lake, but in fact there's a lot going on beneath. So here's a photograph of Annie heading out at sunrise. Rob was driving the small boat. We knew that in order to get some photographs of Yogi and of Annie, we had to get off the vessel itself. It's a very small boat, and it's hard to get the perspective of Annie within the environment unless you're off the vessel. So we rented a small boat, and Rob was driving me around for a couple of mornings as we photographed Yogi at work inside the vessel. It's very, very cramped. It's pitch black. The operators are operating little joystick controls to drive Yogi around. So it was difficult to photograph, but it was the only way that I could show, just what it was like to work in this environment on the lake. This is really, once Yogi was in the water, this was the whole scene for the next, I think, 6 or 8 hours that the vehicle was down on the bottom working. There's another example of a photograph of one of the monitors. So it was they had this incredible bank of monitors which showed everything that Yogi could see on the bottom. And I used, a higher perspective, basically crawling up on top of the lab area on the vessel to be able to get a view of what it was look like as Dave LaValvo here is letting out cable for Yogi to be deployed off the stern of the or off the vessel. Then from the small boat that Rob and I had rented, I was able to use an underwater housing to get some photographs of Yogi going into the water and driving around before dive. So that's how we got these half in, half out shots and beautiful calm day, really early in the morning. I knew it was really important to be able to photograph Yogi. It's once it goes down below the waves, we've got all the video feeds on the vehicle itself, which are showing us what Yogi can see. But I also wanted some photographs to show this amazing technology that was being used to explore the bottom of the lake from the perspective of being away from it. And the second part of the science expedition that I really wanted to communicate, which Rob described, was the coring operation, which happened in September. And so as opposed to all the Yogi operations, which happened in August, September was almost the start of winter when the crew was assembling the platform. Here you can see it's kind of halfway assembled in this photograph. It was actually snowing and sleeting for the whole day that they were putting it together. I wanted to communicate that with photographs like this, showing the kind of environments that scientists are working in. And then once it was fully assembled, again, Rob and I went out in the skiff to photograph the work on the platform out on the lake. By using a GoPro and putting it up on a mount, I was able to get a top-down view of this platform, which shows you just how cramped it was. One of the things I have to be aware of as a photographer is not to get in the way when the scientists are working in these really, really cramped conditions. This was, not one of my favorite photographs, but it's kind of a behind the scenes one showing you just how little space you have to work on this tiny vessel. Just a top-down perspective on everybody that's on that small ship. This is an eye-level perspective of a couple of the team members, securing some of the cores. This is probably right before we were heading in, because you can see some of the storm clouds building, and the weather's about to turn here. But it's one of my favorite shots because it really shows, the science in action, the intensity on their faces as these guys are working to get the work done, just how dirty they are, covered in mud from a long day that probably started before dawn on the lake. Here's another last shot of Rob, getting his hands dirty, working with these cores. I have tremendous respect for Rob and everybody on the science team. They work super long hours for the project, and are not afraid to get really dirty doing it. And so that's one of the things that I like to do for my job, is to communicate kind of these behind the scenes moments, these aspects of the science that don't make it into the scientific papers. They may not make it into the news releases and press releases that go out. But to me, it's a really important aspect of what is science and what it's like to be a scientist. And I enjoy telling these stories. And the last part of the day, after a long day of collecting the cores, I really loved this sequence of shots that I did, because it was, this aspect of teamwork, of everybody coming together. It was lit entirely by headlamp. And this is on the shores of the lake. Scientists hurriedly extracting the cores from the tubes, carefully labeling them and getting them ready for transport so they could be analyzed later. But I always love this moment, kind of just at the very edge of the day as it's about to get dark. They're still just feverishly working to get the cores prepared. And that was just another one of these behind the scenes aspects that I love to photograph. Here's a panoramic photograph that Nathan provided of the exhibit. If you get a chance, once again, I'm going to make a plug to go see it in person, see the photographs, read the captions, because I've got stories that go with each one of these photographs. And I want to thank everybody from the museum for making this incredible exhibit happen. And I want to thank the science team and the National Science Foundation for funding the exhibit. I also want to thank the staff of Yellowstone National Park as well for being really accommodating with both my aspect of photographing the science and for accommodating the science work too. I want to thank Lighthawk and Chris Boyer too for the incredible opportunity to photograph Yellowstone from the air. And if I've left anybody out, I apologize in advance. And here's last slide, just a couple of links where you can learn more. The HDY Lake website has a series of blog posts that Rob and I put together during the years that the expedition was ongoing. Woods Hole Oceanographic Institution's website is next, and then the Center of the West, where you can see more about the exhibit. And lastly is my website.
Excellent, Chris, Rob, thank you so much. I can't thank you enough for again, your time and your expertise and everything you've shared with us. So we'd like to turn it over to our viewers for their questions, and I've got a number of those on the ready. Again, for those of you watching via Zoom here, you can submit your questions using either the chat or the Q&A feature, and viewers over there on Facebook can share your questions in the comment section. So to start off, Chris, since you just ended, I'll give you a second to just enjoy sitting. Rob, how do these vents in Yellowstone Lake differ from or resemble hydrothermal vents in the ocean? Oh, Rob, you're muted.
I see that happen to other people and laugh at them all the time. That's a great question. And the simplest answer is the incredibly large difference in pressure. So, Yellowstone Lake, as we were mentioning, the maximum depth is around 115 meters. So, off the top of my head, 400 feet. For example, one of the places where I dove in the submersible Alvin and had a large field program over multiple years is called the TAG Hydrothermal Mound in the middle of the Atlantic Ocean on the Mid-Atlantic Ridge. And that's at 3,600 meters. So, more than 30 times deeper, and, about 2 miles, if you like the English units better, about 2 miles deep. And so at those incredible pressures, we don't see typically the amount of steam and gas that you see in Yellowstone. Because the fluids are so much hotter and they haven't decompressed, they haven't boiled off a lot of steam. And that has all kinds of implications. One of the things that's interesting about deep sea vents, and this is a little off topic for Yellowstone, but it does kind of circle back. In the same way that if you look at the way different species, on land are distributed, different animal species, you don't see everything everywhere. There's niches and there's a biogeography, as people like to call it. And you actually get that in the ocean. So you have extremophiles that are common to the Pacific, the Northeast Pacific. You have different types that are in the Atlantic or the Caribbean. And so you get different types of flora and fauna depending on where you are, in the same way that you get, different kind of trees if you go across the different parts of the earth. But the main difference is the very, very high pressure.
Excellent. Thank you. Another one for you, Rob. Did the ROVs, AUVs, and instruments require any modification to operate in Yellowstone Lake?
The short answer is not really. There were some. Now, mind you, the ROV Yogi, and I just love that, are the instruments that we put on the lake floor. We refer to them as picnic baskets. Okay. But the ROV was specially designed to be able to work in Yellowstone Lake on the research vessel Annie. So any modifications that you would have needed from a deep sea system were already in place on that. And that was primarily size. Everything had to be miniaturized. I don't know how well you could tell, from the pictures, but Yogi is sort of like the size, I don't know if you stacked 2 picnic tables on top of each other or something. It's something like that size. The ones that we use in the deep sea are more like, a Chevy Tahoe or something. They're much larger. And so there's some miniaturization that had to happen to make Annie work. The AUVs that I showed you, we didn't really need to do much. It's just harder to get them in and out of the water. Because normally we'd be on a much larger vessel with a taller overhead crane and so forth. Probably the main thing, and I hope this doesn't get me in trouble. Anytime someone says that, they're about to get in trouble. But in the deep sea, so for example, one of the instruments that we deployed in the lake was a seismometer. We actually deployed 10 seismometers on the lake floor. I didn't have time to tell you about any of that, but very exciting stuff there. But in the ocean, ocean bottom seismometers, we throw them over the side of the ship, and they have weights on them that cause them to sink all the way down to the seafloor. And then when we want to get them back, we can communicate acoustically with them and send little beep, beep, boop, boop, like little R2D2 sequences. And when they hear that, they respond back, beep, 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 and then they release the weight. So they'll leave a lead weight on the seafloor. And now once they've jettisoned that weight, they're now positively buoyant, like, a bubble or something. And then they rise back to the sea surface and we pick them up. You're not allowed to leave anything on the floor of Yellowstone Lake. And I wouldn't want to, even if I was allowed to, but you're not allowed to. And so we had to modify the instrument so that rather than releasing a weight, it released a latch that would pop up a float, and we'd grab the float and then pull the whole thing up. So there's sort of like a leave no trace, which is different. In the middle of the ocean, you can drop a lead weight. You don't want to do that in Yellowstone Lake. Interestingly enough, that same instrument, the way those anchor releases work is you have an insulated wire, and you you nick the insulation and cut it off so that, maybe a ½ inch of the wire is raw exposed wires. And then when they want to release the weight, you put a voltage across that wire. And because of electrolysis with seawater, because of the salt in the seawater, the wire dissolves. And then that's what releases the weight and allows the instrument to come up. Yellowstone Lake is freshwater, so that doesn't work. You can't dissolve a wire. There's really no salt in the water. So we also had to redesign the release mechanisms. But for the most part, there wasn't a lot of redesign.
Excellent, thank you. Chris, a question for you. You touched on some of them, but were there any particular challenges unique to this trip that made it different from some of the other expeditions you've been on?
Well, I'd say a lot of the challenges were similar, actually. Working on Yellowstone Lake was a lot like working on an oceanographic project, once we were on the lake. One of the biggest differences, though, was actually being in a major tourist location in August on shore. So that was a huge change for my normal kind of expedition or photography trip that I go on. I typically work in areas that are really, really remote. You don't have the opportunity or, to go, to really see anybody else while I'm working. So it's, and sometimes that was great. And, got to chatting with people while I've got, a camera set up on the side of the lake, photographing the lake, or, sometimes it was annoying when you're stuck in a traffic jam and you're, because people are watching bears or something and I'm trying to get down to a location. But that was probably the biggest difference for me was working in this place that had a huge population of tourists there in the summer. But it was really fun overall. I think, it's just such a unique, amazing place. And I got to explore a bit of it, just a tiny bit of it, I think, it's really big. But in terms of working on the boat and on the coring vessel and such, that really felt like a miniature, oceanography expedition. Once you're out there, it's just a matter of not walking off the side of the vessel because it's so cramped, when I'm backing up. That's the main thing. I'm used to working on bigger ships. So those were some small ones. And it had some restrictions. There were a lot of times I wasn't able to go out because there just wasn't capacity on the vessels. So that was a challenge too. That was hard. Normally, you go out for 30 days on an oceanographic vessel, everybody's that's on the vessel's in, that's it. In this case, teams were going out different days and I wasn't, able to go out with every time the boats were going out. So that was just one of those, challenges. Again, as Rob explained, it's just working with size constraints with the lake.
Great, thank you. All right, Rob, I'm gonna try and combine a few questions here into one really big one. So part of it is we've got a group of students who are joining us, and they are wondering when the last time there was one of these big explosions and questioning when, if the research indicated when it might be due to, we might have one of these explosions again. But then to piggyback on that, a few other questions that kind of connected to the research and the coring. Were there any concerns with the coring of breaking through the cap and causing a steam explosion? Did it happen? If so, what were the repercussions?
What was the first question again?
So the first part was just related to those steam explosions. When was the last one?
Okay.
And was there any indication of when there might be another?
Yeah, so I'm just thinking back to that last slide I showed with the stratigraphy. I think the last large explosion in the lake was the Elliot's crater explosion. And I think it was around 7,000 years ago. I don't remember exactly. But this speaks to a very common misconception about volcanic eruptions and hydrothermal explosions. The sense that, you could be due, for one. And it doesn't work that way. It's not like these systems have, an alarm clock set for, 5 o'clock in the morning. Okay, time to, there's no sense of it being due. Okay. And I would say the same thing for the volcanic system, which last had a major eruption 640,000 years ago. But that doesn't really tell you anything about its due. These things have all these processes going on in the subsurface. If it were somehow possible to, CAT scan, like we can take a patient and put them in a CAT scanner and see everything, unfortunately, these systems are underground. And so, as a geophysicist, one of my main jobs, so to speak, is to try to bring that system to light, try to image it using different techniques like seismology or electromagnetics or what have you. So there's no sense that that it's due to have another explosion. I think the smaller explosions that were those little red bars, I think, there's more of a sense that those are somewhat regular. And so, I think we can expect those to be happening in the future. Now, the question is, what would be the repercussion of that? And, if it's a small enough explosion, probably nobody'd notice. What you probably are going to see with these small gas expansion events, what, we think they are, is a great big bubble's probably going to come up through the water column and, on the surface of the lake. As long as you aren't in a fishing boat where that bubble comes up, you're probably okay. But so the things that are pretty likely to continue to happen are not particularly dangerous, I don't think, unless you're just really unlucky. The other part of the question was like penetrating the cap. So we work very closely with Yellowstone Center for Resources, and I probably should have mentioned them earlier because they're so fantastically helpful. But one of their jobs is kind of like a policing function, if you will, to make sure the scientists don't do things they shouldn't do. And, you can't pick up a rock in Yellowstone and take it home without a research permit. People probably do, but you're not supposed to. And if you're a scientist that wants to publish analysis of that rock, you stand to get yourself in a lot of trouble. So every move that we make, almost in a literal sense, we've already cleared it in advance with the Yellowstone Center for Resources. And if there's concerns, we discuss those. In this particular case, we had agreed with YCR, Center for Resources, that we would not conduct any coring operations in active thermal areas. So we didn't. Those 10 to 12 meter cores, those all came from areas that, as far as we knew, were inactive at the present time. Now, all that being said, I had a strong suspicion that there's going to be a steam reservoir under that hydrothermal field. And there are actually some aspects of the study I designed to try and image that with seismic waves, which we haven't finished the analyses yet. So I suspected that was there, but I did not think it was that shallow. And so when we realized that it's only 15 meters below the bottom of the lake, I got a little, chills, like, ooh, that's close. When we were down there, that was closer than I thought it was. So I was surprised that it's that shallow, but we were never going to try to core off the top of that. And the other thing to know about scientists is we tend to be pencil neck geeks, but we have no fear. If there's a sample that we want to get, you see these volcanologists abseiling into volcanic craters to scoop up hot lava with a ladle or something. Scientists, if we get our mindset on getting a sample or getting some data, all common sense can go right out the window.
Excellent, thank you. I have one more quick one that I'll ask you, and then I have a few others that are a little bit more detailed. So out of respect for Rob and Chris, I'll go ahead and pass those on to them and hope that we can get an answer, which we will include in the on the YouTube link in the description. But the last question, in addition to the microbial and planktonic life, did you know any invertebrates or fish during your dives?
Yeah, they weren't. There's a lot of, yes. Okay, short answer, yes. But they weren't really associated with the hydrothermal vents per se. Yellowstone Lake is full of trout. And, there's been an ongoing management crisis because, back in the old days when it was considered trendy for people to screw around with ecological systems, people introduced lake trout to Yellowstone Lake and other lakes in the area to support recreational fishing. And unfortunately, the lake trout have been systematically killing off the native trout population, which has a lot of, if you've ever took ecology, and I'm not an ecologist, but there's a food web, and so there's this cascading effect that it's had on the lake's ecological system, and there's a lot of management efforts going into beating back the lake trout effort right now. But you would see, there's a lot of fish in the lake. There's shrimp in the lake. They're real tiny things. They don't look like anything I'd particularly want to eat. On the fish, I'll just offer one little science hydrothermal factoid. The hydrothermal fluids that are discharging into the lake are very, very high in arsenic and other things. But I mentioned arsenic because arsenic can be toxic. And so the arsenic levels in Yellowstone Lake are elevated above what you would normally see in a freshwater lake by a fairly significant amount. Bottom line is, if you go to the lake hotel or something and you want to order the trout, you're okay. You can eat a trout from Yellowstone Lake, like one. Don't eat trout from Yellowstone Lake for dinner every night for a year or something, because there is a higher level of arsenic that gets into the tissue of the fish.
Excellent. Chris, Rob, thank you both so much for taking your time out of your schedules to visit with us and share your knowledge, your experience, and clearly your passion for your work. Another big thank you to our sponsors, Sage Creek Ranch and the Nancy Carroll Draper Charitable Foundation, for their support of the Lunchtime Expedition Speaker Series. Just a reminder, and I've shared the link in the chat, that this presentation has been recorded and it will be uploaded to our YouTube channel. And if you missed anything from this or would like to share it with someone, you'll be able to find it there. Stay tuned for email updates on upcoming Lunchtime Expedition speakers. If you've registered for the webinar, your email has been added to that list, which you can unsubscribe from at any time. If you aren't on that distribution list and would like to be, let us know by shooting us an email. Again, Chris, Rob, it's been a pleasure having you join us today, and thank you to everyone who joined us from all over the place. Be well, and we'll see you for the next Draper Lunchtime Expedition. Take care, everyone.